if we go through the activity 1.3, in this activity, they are saying that first we need to take a conical flask, add some zinc granules into it, and also add dilute sulfuric acid to it. Now fix a cork at the mouth of this conical flask with a hole in it and pass a glass tube through the hole in the cork, through the cork. So after a few minutes, as the reaction takes place, we get a gas named we get hydrogen gas as a result of this reaction. So from this activity we could find that hydrogen gas is evolved. So from all the above three activities, we can say that any of the following observations helps us to determine whether a chemical reaction has taken place or not. First is change in state. If there is a change in state before and after, then you could say that a chemical reaction has taken place. Change in color, evolution of a gas, change in temperature. So if any one of these four observations take place, then we can say that a chemical reaction has taken place. As we observe the changes around us, we can see that there is a large variety of chemical reaction taking place around us. We'll try to study various types of chemical reactions and the symbolic representations in this chapter. We'll study the different types of chemical reactions and representation of these chemical reactions using symbols of different elements and compounds. So from activity 1.1, where we used a magnesium ribbon, from that activity we could find that the reaction between magnesium and oxygen gave us magnesium oxide. Here we can say that a chemical reaction has taken place as there is a change in state. Initially the magnesium ribbon was in the shape of a ribbon, and later it turned into powder. Now if you see that the word equation for the reaction that took place is magnesium plus the oxygen gives rise to magnesium oxide. Okay, so the substances that undergo chemical change in the reaction, magnesium and oxygen are the reactants. So if you see here, if we look at this word equation, here we have right hand side and the left hand side. Over the left hand side we represent the reactants, and towards the right hand side we represent the products. So reactants and products are separated by an arrow showing the formation of the product. So the reactants can be one, two or more anything, and the products can also be one. The product can be single or it could be more than one as well. So in this case we have two reactants, namely magnesium and oxygen, giving rise to magnesium oxide, a compound. Two elements combine into form and give us a compound. The substances that undergo chemical change in the reaction 1.1 are magnesium and oxygen. These are called as reactants. The new substance is magnesium oxide formed during the reaction is called the product. So this is a new substance that is formed after the reaction between magnesium and oxygen. A word equation shows change of reactants to products through an arrow placed between them. So if you observe this word equation here, it shows that the change of reactants to products is represented with the help of an arrow heading towards the products. The reactants are written on the left hand side, which I already told you, with a plus sign in between them. Similarly, products are written on the right hand side with a plus sign between them as well. If there is only one reactant, then one product, then there is no use of plus sign. If there are more than one product, then we have a use of plus. The arrowhead points towards the products and shows the direction of the reaction. That is the reaction taking place from the left hand side to the right hand side. That is from the reactants towards the products. I hope you understood this para. Now coming to writing a chemical reaction. We have written the word equation, which is not always comfortable for us writing for very big reactions, right? So let's find a new easier method. Is there any shorter way of representing chemical reactions? Chemical equations can be made more concise and useful if we use chemical formulae instead of words. Writing words is okay, but writing for more other chemical reactions like chemical equations, for example, when you go to a laboratory to perform a particular experiment, it involves many of the reactions, equations, and it is very difficult for us to write each and every equation in terms of words. So we use different symbols which are assigned to them to write a simplest chemical equation. A chemical equation represents a chemical reaction. We have gone through this point at the starting of this chapter, right? If you recall the formula of magnesium and oxygen and magnesium oxide, the above word equation can be written as Mg plus O2 gives rise to MgO. So we know that magnesium and oxygen, magnesium has +2, oxygen has -2. By using the method of crisscross, we get Mg2O2, which is nothing but MgO. Here is how we get the formula of MgO by using the crisscross method, right? So this is how we got the formula of MgO, that is magnesium oxide. Count and compare the number of atoms of each of the element on LHS and RHS of the arrow. Now, if we look at the number of atoms of magnesium, 1, 1. Magnesium 1, from product and reactant 1, 1. But oxygen, we have 2 this side and we have only 1 this side. In our lower classes, we have learnt about a law called the law of conservation of mass, that is, matter is neither created nor destroyed, that is, the number of magnesium atom reacted will give rise to the same number of magnesium produced, right? Is the number of atoms of each element same on the both sides? Obviously no, because we have 2 oxygen on left hand side and 1 oxygen on the right hand side. If yes, then the equation is balanced. If yes, for suppose you have 2 oxygens, if you have 2 oxygen on left hand side also, then you can say that the equation is balanced. If not, then the equation is unbalanced equation, because the mass is not same on the both sides of the equation, right? Such a chemical equation is called a skeletal chemical equation for a reaction. That is, the unbalanced chemical equation is called a skeletal chemical equation for a reaction. The skeletal chemical equation for the burning of magnesium in air is Mg plus O2 gives rise to MgO. Do we call it as a balanced equation? No, we don't call it as a balanced equation, as the number of atoms on left hand side is not equal to the right hand side. So it is a skeletal equation. Now let's learn how to balance an equation, right? Recall the law of conservation of mass that you have studied in class 9th. What does this law state? This law states that the mass can neither be created nor be destroyed in a chemical reaction. That is, the total mass of the elements present in the products of a chemical reaction has to be equal to the total mass of the elements present in the reactants. That is, from the activity 1.1, where we have found the reaction between magnesium and oxygen, that is Mg plus O2 gives rise to MgO. Here the mass of magnesium and the mass of oxygen on the left hand side must be equal to the product, that is MgO, that is formed. That is what our law of conservation of mass states, right? In other words, the number of atoms of each element remains the same before and after a chemical reaction. Hence, we need to balance a skeletal chemical equation. Now, let's try, let us know how to balance a skeletal equation. Okay. Here we go from activity 1.3, the given reaction zinc plus sulfuric acid gives rise to zinc sulfate plus hydrogen. The above word equation may be represented by the following chemical reaction. So this is the chemical reaction for activity 1.3. In this, let's count whether the number of atoms on the left hand side is equal to the right hand side or as well. Now, zinc, it's 1 and it's also 1. Hydrogen, there were 2 hydrogens. Here also there were 2 hydrogens. You have 1 sulfur, 1 sulfur. We have 4 oxygens and 4 oxygen. So hence we can say that this skeletal equation is a balanced equation. This skeletal equation is a balanced equation. Let us examine the number of atoms of different elements on both sides of the arrow. The same they have given. 1, 1, 2, 2, 1, 1, 4, 4. Right, as the number of atoms of each element is same on the both sides of the arrow, so we can say that this skeletal equation is a balanced equation.